Okay, so welcome back to another video. In today's video we have the following geometry problem in terms of area. So what percentage of either circle's area is shaded? So here we have like the little design of a Venn diagram, and here we have the little center that's closed in with the shaded area, and we want to calculate the percentage of this shaded area being inside either one of these circles over here. There's two ways you can actually approach this. Of course, there's also there's the geometric approach, which I've never done myself. Well, I wouldn't really say that I attempted, but it really leads to a lot of confusion on how else you're supposed to how to proceed forward with the problem. So another way that I did, and of course that's the second way, is to actually take this into a calculus approach, which in turn you can actually use the definition of integrals and calculate the area beneath the curve. Specifically, since we also have like the Cartesian plane over here listed with the x and the y-axis, and you'll see that with the origin described from here, that the distance between these two points with the two circles combined together, that they're the distance equal to r. So it's just one little detail just to add to that in order to make the the problem solvable. So of course I went for the integral approach, and I don't want to give too much of how to tackle this problem. I think this whole video will just make things like very interesting for you guys, specifically if you want to take into another approach with how you want to solve problems like this, for example. So with that, let's actually just jump in. Okay, so we see that we have two circles. They intersect each other such that the intersection here is shaded. And of course, we're given the question on what is the percentage and how we're supposed to do this. So I said we're going to take this into a calculus approach. So first thing we want to see is that with the Cartesian plane described over here, what I can say is that we can actually model the equation of a circle, since one of the circles actually has the origin at the the center is at the origin. So we know that for the circle equation is described as x squared plus y squared equals r squared. So the radius, that's why we have this right here. So if we were to solve this, we can actually find this in terms of y. So our y is equal to, so if we solve this can be written as the r squared, or the square root of r squared minus x squared. So the way we're going to do this is that when we're calculating the area, what I want to do is let's just focus on the top right quadrant of the circle inscribed over here. And what I want to do is we actually want to take the using definitions of integrals to calculate what's underneath the curve. The way we see this is we need to figure out like what our bounds are. But this is easier said than done to see that if we're calculating the area of the center over here that's intersect the two circles, the intersection really. So what I can do is I can split this area into 4 parts, so it's by quarters, and we see that the distance between r to 0, so the midpoint between the distance here is r divided by 2. So what that entails is that what I can see is that if the midpoint is drawn like over here, for example, then that means I can actually use our, say that we can use the bounds from r over 2 to r, and then calculate the integral over there. So that way we have the area of just this specific part of the quarter region of the intersection over here. Then multiply that by 4 just to get the total area under here. So with this, so I can write the integral. So this is r divided by 2, and then r, that's our bounds. And then with our function that we set over here, y is equal to, so the square root of r squared minus x squared, then dx. Now, of course, you can't really do u-substitution. That's not going to make things any easier. And even if you were to take this into using the geometric approach of calculating the integral, since there's a well-known, everybody knows about that Calc 2 integral where you have the square root of 1 minus x squared, which is just like, I'm just naming 1 for example, which is just the top half of the circle with radius 1. So you just use that geometric approach using the areas of the circle and calculate that. But things are going to be a little bit different over here. So what we can do is we can actually use a trigonometric substitution, and we'll use the following substitution. We'll say that x is equal to r, the parametric equation, of course, the r times sine theta. Well, how about I use sine of u for this, just for the sake of my naming convention. Now, if we were to solve this for u, so that means I can divide r to both sides and then take the inverse of sine. So that means u is equal to arc sine of x divided by r. And of course, over here I can actually just differentiate both sides. So dx is equal to r cosine of u du. So now we can actually do the substitution. So we got to calculate our new bound, since our new integral will be in variables in terms of u. So if I plug r into here, so that means arc sine of r divided by r. Arc sine of 1, that's pi over 2. And then if I plug r over 2 for x, so this is just arc sine of r divided by 2, so that means it's just 1/2, so therefore this is actually just pi divided by 6. So now we just plug in the substitution over here, so I'm going to just do the work right here. So if I plug r sine square, so that means this is r square, subtract with x square, plug this here, so we get r square sine square of u. That's also the same thing as, so I can factor out an r square. So this is 1, then minus sine square of u. But we know that 1 minus sine square of u, using your trig identities, that's actually the same thing as cosine square of u. So r square cosine square of u, and so that's actually just equal to r cosine of u. So I'll just put that back in there, but then don't forget to multiply your dx substitution, r cosine u du, so therefore it's just square, r square, and then cosine square of u du. Okay, and now next over here, what I can do is I can actually, we can actually use another following trig identity for cosine square u and say that that's actually just equal to 1/2 plus 1/2 cosine of 2u. Since 1/2 can be factored out and it's a constant, so I can just put that outside the integral. So even the r square including, since that's also a constant, so it's just r squared divided by 2. Then the integral from pi divided by 2, and then pi over 6. Of 1 plus cosine of 2u du. Next, we can calculate this integral. That's very easy to calculate. So I can actually just split this up into linearity, just make things easier. So we'll do the integral of 1. That's just u. So it's from u, evaluate from pi over 6 to pi over 2. Then we add this with r squared 2, then let's see, cosine of 2u, so we do u substitution, let u equals 2u, divide by that, so it's 1/2, and then integrate that, so that's just sine of 2u, and then divided by 2, evaluate from pi over, that's pi over 2. I divided by 2, pi over 6. And now this is easy to calculate, so r squared 2, so this is just pi divided by 2 minus pi divided by 6. Add this r square, I'll factor out the 2, so this is just pi over, or r squared divided by 4. Let's see, sine of 2u, so 2 pi, so the sine of pi, that's, sine of pi is just 0, then subtract this with 2 times pi over 6, so that's pi over 3. Sine of pi over 3 is actually just the square root of 3 divided by 2. And then we can actually do the calculation over here, so r squared 2, inside here pi, if we get this under common denominator, so let's see, pi over 2, so that should be pi divided by 3. Then I can add this with, let's see, r squared, then 4, then this is just minus square root of 3 divided by 2. Keep going further, I can actually write this, we factor out r squared divided by 2, so r squared divided by 2, this is just pi divided by 3, and let's see, subtract 2, so and then subtract with square root of 3 divided by 4. Okay, so that's our area for the quarter region. So now if we just multiply this by 4, then we have that, so just 4 over here, so then this is just 2r squared. And then next, you just want to find a common denominator under one fraction, so this is just 4 pi, subtract with 3 square root of 3, and then divided by 12. You can simplify this out even further. This is just r squared, then multiply with 4 pi minus 3 square root of 3, and then this is just divided by 6. So we have shown that this area is actually just equal to the intersection area under here, but since we're asking for a percentage, so we had to calculate the ratio. So what that means is that if we take our intersection, the area intersection over here, and divide this with the entire circle, either one, so obviously we know that the formula for like the whole circle is pi or squared, so I can just take this and then divide by pi over square, and then we get our ratio. And since it's in terms of percentage, you just multiply the 100. So that's basically the last step that we need to do. So now, next, or rather lastly, well, how about this? I'll take this step here, then we just divide by pi divided pi r squared. Then if we do the work, then r squared cancels, and so we're just left with 4 pi minus 3 square root of 3, then divided by 6 pi. And then the last part here is that what I can do is, since it's asking for percentage, just multiply 100. So that means the final answer is just 400 pi minus 300 square root of 3, then divided by 6 pi percent. Or in other words, this is actually just equivalent to 39.1%. Okay, so there we have it. The final answer drawn in this red box like so. All right, so yeah, that's pretty cool if you ask me.